and welcome. We have made it to the last class of the day. And if you've been like the rest of this industry of rock stars that has somehow done these conference all day and then partied maybe a little bit late into the night, this has been a really great time of collaboration and knowledge sharing and all these pieces. And when John Travacco goes, "Hey, Brock, I got this idea for this global perspectives on geothermal drilling. And as he's traveling and seeing these different technologies, I got really excited. And I'm like, yes, I too, traveling, get to see other perspectives of drilling or how we're doing it and the implementation of geothermal across the world. And at the same time, he goes, yeah, just set up a call with these four guys and we'll get it going. I get on Google and I'm like, wait, Soren's in Adelaide. Yeah. Yanni's in Scandinavia. Geoff's in the UK. I don't even know where Tunca was at the time, but I don't know how to schedule this call. And Soren comes back with this spreadsheet and he goes, listen, it's going to be 9:30 p.m. for me. It's going to be 12:30 for Geoff. I don't know what time it was for Yanni, mid afternoon. Yeah, and it was 8:30 for me or 8 a.m., I guess, for me. And so as we pull this together and we have all of these great individuals to share how it's being done elsewhere in the world, like I grabbed my dodgeball shirt because bold strategy, John Travacco. Like, let's see how this was going to play out. And so we have these great individuals today to share their perspectives and knowledge. And that's what's awesome about geothermal right now is we are better together. And as you look at what France is doing and the implementation for drilling programs in adoption to Luxembourg and Belgium and the Netherlands into how Rototec and all of, Sweden and Norway, and I'm a dumb American and I'm going to start lumping in wrong countries that are supposed to be there. But, you know, we've had great acceptance and adoption elsewhere. And so here we have it today, and we're going to have some great perspectives. And I'm going to let them get up and introduce themselves and go through it. And then let's ask some great questions because let's launch New York-GEO 2025, the last session out on a bang. So thank you. I'll let Johnny come on up.
Okay, good afternoon, and thank you for inviting me here. I'm Johnny Lönnroth from Rototec, and I'm going to explain how we do geothermal drilling in the Nordic countries, specifically Finland, Sweden, and Norway. Uh, but let me start with first introducing myself and Rototec a little bit. I myself have worked for Rototec about 6.5 years with various tasks in analytics and consulting. Before I came to Rototec, I first did a PhD in physics. Then I worked for a while in nuclear fusion, then in management consulting, and then somehow I ended up in geothermal. So quite an interesting journey. Rototec, in brief, we are a geothermal drilling company, but we are actually more than that because we also do quite a bit of consulting in geothermal. We are present in 5 countries now. We've traditionally been since 2007 in the Nordic countries, but now we are also since 2 years in the USA and since last year in Germany. We drill about 6.5 million feet of energy wells per year, and we have a fleet of about 66 machines. So that's briefly about us. Let me explain how we do drilling in the Nordic countries. And this picture here explains it a little bit. So we typically use this kind of small track-mounted, easily maneuverable drilling rigs, with which we drill. Then we have a 35 bar or 508 psi compressor, and it's all mounted on a single truck that we drive around with. And it's operated by a single driller typically. We use the down-the-hole hammer drilling method because we drill in hard crystalline bedrock almost always. And we drill 4.5-inch boreholes, so fairly narrow boreholes, and when we drill the casing in the overburden, we use 5.5-inch casing. We drill the casing about 6.5 feet into solid bedrock and anchor it there with bentonite cement. That seals also the surface water off from the groundwater. And the rig is a single head rig because we leave the casing in the ground. This is a fairly efficient setup so that one driller with one drilling unit typically can drill about 1,000 feet in a day. Then let me explain how we deal with cuttings and drilling water. So the cuttings are always collected in a skip like this, as you see in the picture, or dumpster, as you tend to say in the US. We take the dumpster to a dump site and empty it there. And in this way, we always keep the work site clean and nice. The dumpster is also used for filtering out sediments from the drilling water. So we then lead the drilling water out from the dumpster, for instance, into a storm drain. However, sometimes you require greater levels of purity, and then we have our own water treatment systems for cleaning out the drilling water. They are shown here. We have two products for which we are seeking a patent. We call them Rotocont and Rotocont Plus. And essentially, they work so that you filter the drilling water through numerous filtering compartments, and then out goes a fairly clean product at the end. Then let me explain a little bit about how we tend to design our borehole fields in the Nordics. So we use fairly deep boreholes. The typical depth of a borehole in a commercial project would be somewhere between 1,000 and 1,300 feet these days. The boreholes are almost always angled in large projects where you have multiple boreholes. And we place the borehole tops typically about 65 feet apart if we use heating only. This is so that the boreholes don't cannibalize each other too much. If we mix in heating and cooling, we can have the boreholes closer to each other. But this figure here would show what it would look like in a design. So the small black circles that you see there and there and there, they are borehole tops. And then if this is the top of the well, the bottom of the well would be at the end of this projection that you see here. The dotted circle here indicates the effective area from which the borehole would suck its heat energy. And it's these circles that we try to space about 65 feet apart. The circle is centered on the midpoint of the projection. So of course, the borehole tops can be closer to each other, but like the average spacing is what matters. Then we connect the boreholes in groups into manifold chambers. So in this design, for instance, we have one manifold chamber here and one manifold chamber here. And the boreholes, these boreholes up here feed into this manifold chamber, and these down here feed into the other one. And then the manifold chambers are connected with main pipes that feed into the mechanical room. And that's a fairly typical design for the Nordics. That's good. Grouting. Well, the short answer about grouting is that we normally do not grout. This is because we have crystalline bedrock with only typically isolated fractures. So the authorities generally deem this practice of not grouting as being safe. We also use bioethanol, which is biodegradable as the heat-carrying fluids. In the rare instances that we grout, we tend to use pre-mixed cement-based grout with quartz sand, which is great because it has great pumpability at different temperature ranges. But it's only typically if we drill in water protection areas that we have to grout. Normally we just let the borehole fill up with groundwater. Then a little bit about how we design pipes and this design with manifold chambers. We typically use very thin-walled pipes, pressure category PN10 SDR17. This partly has to do with the fact that we do not grout. The vertical loops would be more or less the same that I used here. We use inner diameters of 1.39 inch, 1.56 and 1.74 typically. And then the main pipes would have larger diameters. As I said, we connect the boreholes to manifold chambers, or you can also have manifold cabinets like this, as this slide shows here. So you have typically about 12 boreholes feeding into the same manifold chamber, and then the manifold chamber feeds into the mechanical room of the building. And this is a fairly efficient way of doing things. Using manifold chambers and manifold cabinets has a lot of advantages. It's quite easy with them to control the flow through each borehole and maintain a stable flow through the boreholes. If there is a leak in a single borehole, it's fairly easy to isolate it because you have valves on this manifold, so you can simply shut off a single borehole. You can get rid of microbubbles from the system quite easily. You do it so that you leave only one borehole active, and then you flush this borehole, and so you don't need an awful lot of pumping capacity to get rid of the microbubbles. This is a fairly efficient way of doing things in the sense that it tends to require fewer feet of piping than competing solutions. It tends to require less excavating. It tends therefore also to be better suited for urban areas. It's also quite easy to expand a system like this. You just add another manifold chamber and you can add more boreholes to it. And it's also, if you have, for instance, borehole thermal energy storage, you can easily create temperature gradients in your system by playing with the valves in the manifold. And if you use manifold cabinets, you have the additional advantage that the manifolds are not on the ground, but you can have them, for instance, in the mechanical room. Now looking at the time, I think I have used up my 10 minutes, so I'll hand on to the next speaker and then we can take questions afterwards.
Oh, and this won't take 10 minutes because John Cavacco's already sabotaged my presentation by telling me not to repeat what I said this morning. So he's rather truncated my act. Okay, and we had a good chat this morning about grouting, and so we'll leave that one out as well. Okay, what John did say was to talk about grouting and testing. I have a company called Dragon Drilling, which is a Welsh-based drilling company. We also have a plant hire business, and we were talking this morning about an automated system for testing loops. So, John said, what's a typical borehole in the UK? Well, not dissimilar to yours, I don't think. We're talking about 6-inch diameter, although we tend to work in metric these days. Typical depth, 300 to 600 feet. Spacing, when we have multiple borehole systems, about 20 feet. And our loops are SDR11 polyethylene. That's got I put 40 mil in there. I think that's 1.57 inches OD. And in the UK, virtually all our boreholes grouted. The only place we don't grout boreholes is in northern Scotland. And the reason for that is because it has the same geology as the Nordic countries. So we work on the same principles as they do. I was going to talk about drilling mods and how similar they are to grout, but we'll skip through that because there's no point. So in terms of our grouting, okay, mixture of powder and water. We always use pre-mixed material to make it nice and consistent. The basis on that is if we have the amount of water, mix it thoroughly, then we are complying with what the design has requested. What we do to test, we're not talking about a rigorous test regime. We're talking about just using straightforward specific gravity. So we're already using specific gravity testing for our muds. So it's merely a case of transferring that expertise onto our grout. And we always test the grout which we're pumping. Okay, we don't want the stuff in the batch. We want to use the actual material we're putting into the bore. And the grout type and the density specification is always prepared and given to us by the designer. We don't think that out. We're not that smart. We only follow instructions. That way, if it's wrong, it's his fault. And we find that to be an accurate test method for use in field conditions. And that's what we're talking about. We may be sending samples away for testing for conductivity, but as a driller, what we can work on as a drilling organisation is what we're playing with, which is the material we're putting into the ground. Insulation, we use sacrificial trimming pipes. We spoke this morning and you seem to raise your pipes up as you grout. Ours are attached to the bottom or just above the bottom, strapped down, and we simply administer it from the bottom. The reason we do that, grouting bottom to the top all the way through, is because we are trying to displace the groundwater. We want a nice consistent grout at the bottom, and we pump like hell until we have grout coming out the top. Initially, it's water, then it's a mixture of grout and water, and then it's grout. And we test that grout as it comes out the ground. If it's the same as what we put down, we know we've gone from top to bottom. And on that basis, we also charge by the bag of grout, not by the meterage or the footage, because we often use way more grout than theoretically we're going to because we're filling voids. And our drillers then make a photographic record. So that's a finished product. That's what he's done. That proves he's got to the top, and we submit that as part of our records to the company we're working for. Now, we had a bit of a shock in October 2023 because our government in England described heat then as a pollutant. Now, if you have a potential pollutant in the UK, it's covered by our environmental permitting regulations, which means we needed a permit for every single closed loop system that goes in the ground. We always had permits for open loop systems because that's a groundwater activity. So that put the fear of God into everybody. So we need a closed loop installation we needed an environmental permit for that. And then as I scoured my way through the legislation, I found the escape clause. The escape clause was that if we were to name standards, we can avoid direct permitting. So the next thing we did going through the legislation was find out what the standards were. And 3 of them were produced by the Ground Source Heat Pump Association, which is our trade operation in the UK. That's the vertical borehole standard, the horizontal one, and also the thermal pile. And the other standard they named was BS EN 805, which is a pressure test for making sure the loop doesn't leak. So, Ground Source Heat Pump Association standards deals with the entire project. The design, the materials you use, how you install them, and how you test them. The pressure test is a straightforward BS EN 805. Those of you there some morning would have seen how we do that one. And the flow test they insist on is that the design flow rate in both directions without disconnecting the pipework. All of the GSHBA standards cross-refer to UK safety regulations. So the government have nicely combined their both environmental legislation and safety in one fell swoop. So it's now a legal requirement in England to comply with a GSHBA standard for a closed loop installation, unless you want to go and get yourself a permit. We don't know what they're going to do in Wales or Ireland or Scotland. They're still thinking that one through. They've been thinking it through for 18 months. I'm not sure when that's going to be finished off. So, incentives from the government. We claim a $5,000 payment for any system under 150,000 BTUs. But to qualify for that, we have to use a certified installer and certified equipment. Okay. And in terms of how do we get that? they've decided to extend the certification process, not just to cover the installer and the equipment, but also the driller himself. So we now have a external audit of the driller, which qualifies for 2 years certification. That audit is in two parts. The first thing that the audit consists is a desk study, where information on the driller is submitted to the auditor. That will have his qualifications, his experience. It also will have information about the company, insurance policies, examples of their meta statements and risk assessments. So the audit proper will not start until that procedure is in place. There's then an on-site audit by an experienced auditor, and he will ensure, first of all, the equipment works properly. He will check things like emergency stops, guarding, and he will then assess the driller for his competency in terms of his drilling ability, how he handles loops, how he grouts. That is voluntary at the moment, but later on this year that will become mandatory. And in that situation, if you want to qualify for your payment of the $9,000, you then have to extend your permitting application to include not just the equipment that's in there, but also the driller himself. So for the first time, the entire project is covered by effectively an audit procedure. That's my bit. You've been waved your notice at me, so that's less than second period. Okay, thank you, Geoff.
Yeah, thank you for the invitation to represent Australia today. And as you probably can hear from my accent, I'm from Scandinavia too. I don't speak like Crocodile Dundee yet, but I'm working on it. I've been in Australia for the last 12 years, and I can only start by saying that ground source heat pumps is not yet a big thing in sunny Australia. I can say that at the end of 2023, we still had less than 100 megawatts of ground source heat pump capacity installed around the country. So it's evolving in development. The methods we're using in Australia are pretty similar to what you do in New York on the wide scale in terms of borehole sizes and depth. And we grout all our holes up when they are drilled. But so I'm going to talk a little bit about something else that we are big about in Australia, and that's going to be drilling, especially drilling productivity and drilling safety, because that is a really big thing in Australia. I just will start by saying, as we saw on the drilling show on Tuesday, that all drilling today, also in Australia, uses a range of drilling rigs that all has the same thing in common. They're using drill rods. And that's no matter whether they're drilling with mud rotary, air hammers, or sonic systems. And just as an example, if you would be drilling a 575 feet hole using 20-foot rods, you would use about 30 rods, to get to the bottom of the hole. If we were using the rig that we saw on the drill show on Tuesday, that number would be 60 drill rods to actually get to final depth. When you drill with drill rods, you have to start your drilling process and stop it every time you add or take a drill rod away. And no matter how you work that out, it could easily take you half an hour just adding drill rods to and from it, going down to that depth. And if you want to come back out, it's about the same time. The 10-foot drill rods that were used on the drilling demo on Tuesday are a little bit quicker to add on than the 20-foot rods, but there will also be 60 of them that you have to add to get to 575 feet. It can take a bit longer, even if you have rod handlers or not a number of people helping slinging the rods. So you can easily spend an hour just handling drill rods in one of those holes, just as a reference. And it's also not to forget that is exactly 46% of all reportable injuries on drill sites in Australia, and that's not just geothermal, that's all drill sites, originates from drill rod handling or rotating drill rods. So what are we doing different in CoilRig? We have increased productivity and safety by adapting coil tubing drilling
which we are doing now in Australia. We've replaced all the many drill rods to get to the bottom with one single drill rod, and that's what we call the coil tubing. Coil tubing has been around for many years, mainly in oil and gas. And the coil tubing is basically what you can see on the funny looking reel on the back there, and the black tubing you can see on it there. That's actually our drill string.
Really?
And we've developed smaller and more compact coil tubing units, and they've been designed for various applications, especially for mining exploration, but also now for geothermal drilling. And just let me clarify what I say by using coil tubing. We also use steel pipe for drilling. I mean, in our most standard rig, we're using a 2 3/8 high tensile steel tube with a wall thickness about a 1/4 inch or thicker. So just to be clear, this steel tubing that we are winding up and down in the borehole, it's not plastic, it's not carbon fiber, it's not a hose. It's a high tensile steel that we by brute force stretches and bends back on the reel while we are, you can say, pulling in and out of the borehole. That means we have no start and stop of the drilling. The circulation of fluid or air, what we're doing, is consistent. We don't have any spinning drill rods on surface, and also we don't have any external rod handling except for that reel that you see in the middle of the mast there. And also, we don't have any rotating drill rods like conventional rotation heads or sonic heads or whatever, but they are then replaced by two other components that we need to do it. Firstly, we have a downhole motor, which from the outside looks a little bit like a drill rush, but it's actually attached to the end of the coil tubing. And those downhole motors are also known as mud motors or drilling motors, and it's a hydromechanical rotation device that's used in many other drilling applications. It's powered by the drilling fluid that we are sending through the coil tubing, and is pumped inside, and that fluid powers the motor by converting it into to rotational movement. And that's how we basically, with a bit on the end, we do the drilling there. And if we are into the hard bedrock that you've been talking about, we also add a percussive hammer, but we're not drilling with air, we're drilling with a fluid. The second component is the injector, which is a crucial part of that drilling. And the primary function is to push or inject or pull, retrieve this continuous coil tubing in and out of the borehole with force, precision, and control. And this injector, it grips the coil tubing with force and move it up and down. And our injectors, of course, made for drilling, continuous drilling operations with some high torque. Once we have completed the borehole, we are at the bottom. We can pull it out and we can coil it back on the reel, as we call the thing on the back there. And that we can do really quick. So it doesn't take us half an hour to come out of a borehole. From these 575 feet, it won't take 30 minutes or more. It takes us just about 4 minutes coming out there. And if we want to go back in the hole, let's say that something has collapsed in the bottom of the hole, it also only takes us 4 minutes to go back in and re-drill it if we need to. What normally happens then is that the motor and everything stays on the rig, and then we have the possibility to use a stinger if the driller chooses to help or assist to install the ground loop to install the loop in the ground. Bending and stretching that steel all the time. Of course, it will fatigue at some point in time, like a paper clips. But our rigs are designed in a way that we can complete between 300 and 600 installations with one drill strength for that we have for the normal sizes. We can't always get away from not using casing. We can get away with way less casing that you do with drill rods because we have this constant flow in the borehole. But we can have an optional rotation head sitting in the mast that we can make available in a few seconds if we want to install some casing or drill with drill rods. And also our mast can go up and down, and we use that when we're installing the casing or installing the longer tools. What we do in terms of controlling the rig will sometimes split the drillers in two, those that can accept and live with remote control operations, and those that would like to stand with their hands on the hydraulic levers. And that's a bit of a discussion. I know that among drillers, but we can then get away from the rig in a safe distance because it is a hands-free drilling method. It's not like you saw on Tuesday, for those of you in the drilling demonstration, where you have people slinging drill rods. The driller can stand away and just do the drilling. And a really, really productive good day on a coil tubing drill site is extremely boring because there's not really anything going on. You just see that tube going into the ground, and you even have to explain to people what's happening here. What it does provide is that we have a number of data points. So we can log exactly what's going on. We know what depth it is, and you can sit back in your office and look on your phone and see what's going on the drill site if you want to do that. Also, coil tubing presents its own challenges, but also because we have this control system that ensures that we have a very straight drill string as it goes into the ground when we're drilling, which is important for drilling a straight vertical hole. So all these advantages and all of that, what does it actually mean? I mean, us not having to add all these drill rods going in and out of the borehole, it means we save the time for the connections. And what we see in straight benchmark comparisons with drill rigs drilling next to ours is that we can have a 30% productivity improvement for the same time, because we're basically having more time on bottom when we are drilling. Also, it's continuous, so our borehole completion rate, when we're successful with the boreholes, is much higher, which leads to us, unless it's required by legislation, we can get away with much less casing. We don't have to put it in, we don't have to take it out. Again, it saves time. And of course, the safety enhancement, we don't have all the rods and rod handlers that squeezes our fingers, so we're free of that. And also, yeah, it's a single person operation, as Johnny talked about. It's a single person operation on those rigs, but it definitely is also here. In the future, we could actually see one operator maybe looking after more than one rig at the time. Yeah, you can see from the video a little bit what a setup could look like if it was in a suburban area. And on this animation here, we actually made the cars drive in your side of the road just so that you could see it wasn't Australian. And so, I mean, we found a number of benefits that we have done because we've been doing this kind of drilling in Australia for the last 10 years, but especially the last 5 years. And there's a number of added benefits that just come with this way of drilling in terms of energy efficiencies and so forth. All right, that's what we do in Australia. And we'll have some of this stuff in this neighborhood shortly. So we'll see how it goes in New York. Yeah.
Last but not least, Tunca with Celsius.
Thank you. Yeah, so the last day, last session, last speaker, you made it, guys. So I think that's awesome. So let me move this. All right. So my name is Tunca Alikaya. I am from Turkey. I'm Turkish. I'm going to be talking in the US about French and the UK drilling operations. So it's quite diverse, background that I'm going to be sharing with you. So just to give you a little bit of context, like how I get into this business industry and how and previous industry and experience has a transformative impact in the knowledge sharing and capabilities. I started my career in France, in Paris. At that time, it's called Schlumberger. It's an oil and gas services field company. And then I moved to Germany and then Africa for 3 years, and then Eastern Canada and Guyana before I come to US. So I was doing mostly directional drilling and as well as the measurement while drilling. And as a field engineer, then move up in the corporate ladder in the management roles. So I came to US around like 2021. That's where we started expanding our, French operation to the US. And we started in France in 2021 as a Celsius Energy, and we gradually expanded to the geographies. First of all, the US and then the UK. So that is the some practices that I'm going to be talking about from those locations. I know that we were the last session, so I will try to reduce the cognitive load on you folks. So these are the 3 points that I would like to talk about. The first one, the inclined design angle drilling. It's been told a lot of from my colleagues here and my counterparts. So why we do angled for what purposes is to really give the client to a space and flexibility in terms of the surface. So the 90% of the space reduction and the site impact can be avoided with the angle drilling. Imagine the conventional drilling techniques, vertical. We drill from 2 car park size lots in the same size, and then we drill for a different angle. So that way we can reduce and we can give back the client to the occupied space on the surface. And the excavation and the remediation is a cost associated with that one. It has a big impact, especially in the US and as well as in the France and the UK. So we give back that as a cost, and as well as the lateral connection size. So you imagine the vertical borehole, you're connecting each and every pipe, but if you are co-locate the bores in one place, you will be reducing that piping and as well as the cost associated with that one. By the way, all the things has a cost impact. So it's goes back to John's point that like and Caddy's point actually from the line that reducing down the cost, make it simple, so that way this technology can become competitive against the other ones, the electricity and the gas. So it has a huge impact. It might sound like a small, or like the other ones that I'm going to be talking about might be insignificant, or maybe you find skeptical, but the minor impacts overall compound to a big impact, especially if you're operating in a big operations, more than 2+ or 3+ rigs in a different geographies. So it really pays back to you, and then you reflect to the client, and then everybody benefits on that one too, and then you bring down the cost, so it deploys in a mass scales. So the incline is pretty obvious. When we first came, it was not that obvious, but glad that the market adopted and our competitors, everyone is loving it. So we going all in. So that's great. Kudos to everyone. The second one is it's data analytics. So back in our old historical background that I'm working with, data analytics is a big piece. So we measure everything, and the measurement has a huge impact because you cannot know what to improve if you don't measure. So it's a black box. So what we do in our operations, both in France and UK, we measure each and every detail from rotation, from downhole trajectory, from pumping from the ground, or any other IoTs that we can implement to the system. So we know what's going on, like even including the fuel consumption or anything. So we have an idea about what the big picture is, and we know where to squeeze it. And it's going to help. Again, I'm coming back to the bottom line, but it's going to help you to contribution margins of the project. So that's the analytics piece, and then the third one, which my colleagues mentioned as well here, the premix crowd. I think Johnny, you mentioned, and you folks as well there. So the premixing is one of the things that we do in the France predominantly. Sometimes not in the UK, but like it is removing the some burden over the field operation, and so that way you can reduce the crew size and you can again be more competitive in the operation. So the having that load removed from that field operation has a great impact, and I know we can do it in the US, but there's a good learning from the French sides that it's doable, and there are a lot of techniques. So those are the 3 things. This not the exhaustive list, but I think these are the things then US can start deploying and start thinking about it. You like it or not, but it's a different way of looking at the things. So I would like you to give the last few moments with the projects that we have delivered First of all, it's one in the France. It's one of the biggest in the France. I think it's one of few, in the projects in the whole Europe. The project is in it's called the Ferney-Water in Ferney-Water, France. It is part of the system with the same design system with the CERN, the particle accelerator. So that CERN particle accelerator has a heat byproduct. So that way we can use that heat byproduct as a feeding the system and feeding as a thermal storage for the design that we have. And here on the left hand side you see the design. This wouldn't be possible. This installation would be possible without the incline system. There are many restrictions around that one. And as you see, it's not only the one size fit for all. Like it's a mixed. It's the hybrid system. So you can have the vertical, and as well as you can have the inclined bore too. The second one is from the UK. Before moving to France. So France, you cannot drill deeper than 200 meters, which is 660 feet. So if you would like to drill more, so you need to have a mining rights. And it's a pretty lengthy process to achieve that one. So everyone is better off drilling to 656 feet. And they have a great knowledge, country-based system, or like a database that's called BRGM. They collect all the geological information in their system and it's open public. So in the US, for example, if I'd like to, go and assess the drillability or project feasibility, I need to go and look at, many resources. Potentially, I won't be getting a pretty good return on that one. But in France, they're doing a great job. So if you want to drill, they can give you the drilling risk, they can give you the thermal conductivity, they can give you all the parameters that you need for a proper project feasibility assessment. So they do a great job, and we need to learn from these guys on that end. So the second one is the social housing project in Greater London. It's a little bit of north side of the London, and this project is again same thing with that. You can see the design. It is from looking at from the top or from the bottom. It is a mixed. It's not 1 or 0. Again, it cannot be enabled through the conventional design system, and it really lowers the surface construction footprint to almost 1/3 of it too. So minimizing the client disturbance. It really it really helped the project to go forward. And so same thing with the UK, because it's the small footprint for the small country led to the US. They have a pretty good knowledge about the subsurface. It is also coming from the oil and gas too. So at that time in the oil and gas, they have a great understanding about subsurface. So there is not much, no unknown that you go and drill, unlike the US. So they do also, I think it was called British Geological Survey. They do also a great job about consolidating and collecting all the information and then sharing it to the public. So it has an impact. If you reduce the uncertainty in your costs at the upfront, it will benefit everyone, including clients. For different purposes, like in the US, it's more like a grid resiliency, more like energy affordability. But in the France and the UK is more, energy security. And if you think about the energy trilemma, it is their incentives are different than US. So, but whatever it is, we can do better. We can improve. We need to change the mindset around we need to move from this is how we do things here, then should be kind of looking at an open growth mindset. That's, hey, let's try, see if it doesn't work. We move on, but if it works, everybody's like that. Thank you so much.
Okay, we already had a question that wanted to be with Rototec. We still got it. Thank you for being patient. I apologize to. I'm sticking to the John Trabacco rules here. I don't want to get in trouble.
And we're the last session today, so we can go all night.
At Treehouse down the street all night.
Just curious, how are the geo loops suspended in the boreholes with no grout? What do you do to keep it in place? Jason Hertzen during
Question.
Is this on? Yes. We typically use a small device called a slangman, which feeds the loop down the borehole. And then at the end of the loop, at the bottom of the borehole, there's a weight that prevents the loop from floating up from the borehole, essentially.
That's Bracco, Lauren Consulting Engineers. Two questions, actually. The first one, just for the Australia drilling. Is there a cost premium for that operation? Because it seems like it's a very efficient way to do it, but it seems also to be relatively unique to your region. So I'm curious what the cost premium may or may not be there. And then just for the general panel, everybody talks about how they put their boreholes in. What happens if you reach the end of a life for a borehole? What's the process for like capping and abandoning such things? Because I know that's an issue with the oil and gas industry not doing it correctly. And I don't necessarily want to see it bleed over into our industry.
First question regarding the cost of the drilling and the cost of the operation. And I think depending on what area,
Really speak into the microphone, please.
okay, depending on what area you're drilling in, the cost varies for the drilling. But we have done a lot, as I said, in the last 5 years to compare costs to, as we start calling them now, stick rigs, just to sound different, with the coil tubing drilling. And there is significant cost savings in using the coil tubing technology just one-to-one in the same formations. It hasn't been compared in the geothermal industry as well as in the mining and minerals, but we have a number of good numbers in mining and minerals. It's definitely cheaper.
On the life cycle. Who's got something on abandonment, or what do we do next?
Yes, on the abandonment of boreholes. You in Finland you would always, or in the Nordics, have a cap on the borehole. So it varies from place to place, but I don't think the authorities have demanded anything else than that you pull up the loops. But you can, of course, refill the borehole with grout. But I don't think it's usually necessary. But it's also a fairly like young technology in Finland at least. So it's not been done very often. Probably more often in Sweden.
In the UK, we have to submit a proposal to our Environment Agency for them to approve, taking into consideration the underlying geology, aquifers, etc. So everyone is site-specific.
I think that's a beautiful question. And if we look at municipal water, and I spent time with Suez and Veolia as director of wells, we need an operational stages for life cycle. If we're talking 50 or 80 years, we look at our water infrastructure right now, we've screwed up. We're 100 years old and it's failing places. We need to be ahead of this, and it's right now. That's a great question. Next question.
My name is Anthony Stiltner. I'm with Dandelion Energy. I'm the drilling lead for Dandelion Energy. Question is on the angle drilling. So I've asked myself this all week. How much are we doing deviation and azimuth downhole on the first bores, and how much is that playing into the overall scope of the project?
So I can talk to on that just to clarify. So how we operate is how we design is. We design the bores with our design tool, and we have a technological advancement and technological the tools that we take it as a bottom hole assembly. So then we drill with that assembly, and then we measure. Most of the places, the deviation is negligible because we have the system and we have already designed the bottom hole assembly based on our initial assumptions. It is pretty, you're paving the way to paving the line to what you have been designed. So it is negligible. But if you don't have a, proactive control system, the deviation could be out of control. And as you go post backup drilling, you cannot really, pinpoint where is it coming from. Is it formation or your assembly? Where is it coming from? So it needs proactive and pre-planning about how you're going to approach and where you're drilling in terms of formation and geology. And then you go with that, and the deviation is negligible.
So
No, break.
in your sense, you're running a directional motor and a multi-shot, more or less downhole on the BHA. And what my real question, I totally get where you're at, but what my real question is, in the U.S. here, I've been requested on some projects to just kind of angle it and go with it, and I'm like, that bore's not going to go where I'm thinking it.
What?
So how do I tackle that next step?
Yeah. So you need to design the tools that you are drilling with based on the formation that you are penetrating in. So you need to correlate between your formation, your all the specs and the parameters of the bore with the equipment that you have. So I cannot give you like a single answer that you have to do this, but it's like a it's a it's an equation with x to n, different variables, and everything has a different way to calculate the output. So it is not just one solution; it is just a combination of the multiple solutions that you need to implement. So then you go and see it. Like if you see a deviation, then you learn and you change the things. I'm just trying to also allude on that one too. Then you also learn from that one, and then you're golden. So it needs a lot of iteration to come if you are deviating more than that you expect. But I'm talking about the New England formation. It's pretty predictable and negligible to our knowledge.
Come on, Tunca. You wanted to say what every driller says, and it depends.
Yeah.
Can I comment briefly also? So we drill in hard rock, and of course the boreholes can deviate widely, but it's an issue regardless of whether you drill straight or whether you drill angled boreholes. So sometimes when greater precision is required, we have special steering rods, for instance, to make the borehole straighter. And then we also sometimes do straightness measurements afterwards to check what the system looks like in 3D. And then if it turns out that the boreholes are lumped together somehow, you could, for instance, drill an extra borehole or something to compensate for it.
Hi, my name is Mike Fleming. I'm with Phoenix Foundation Company. I've been a driller for most of my career, but I'm just in my current position, stepping out of the field and into the office. I've got a bunch of questions about coil tube drilling.
30 words or less. No, I'm just go ahead, Mike.
It's gonna be I don't know if you'll understand my shorthand. Can coil tube drilling utilize directional motors down the hole?
Yes.
All right. How is the lifetime?
Can I add a little bit to that? Because it actually ties well into the question that was asked before. One of the things that differentiates drilling with drill rods and coil tubing is the continuous drill pipe, right? And it's relatively easy, has been done for many years in oil and gas. You can have communication to the bottom of your borehole, if we call it the BHA. If you want to drill cheap and fast, you don't have any of that in your drill rig, but you can very easily have that where you can survey where you're going. You're a few feet behind the bits, but you can see where you are, and you can steer your BHA as you drill. It slows the process up a little bit, but it can be very accurate.
And that's is that mud pressure you're using to steer?
Excuse me?
Is that mud pressure you're using to steer? Is that
No.
what you're,
No, that's electric.
no.
You're not breaking connections, Mike. So
Right.
you can have continuous line to it
Correct.
through the coil.
How is lifetime of the drill string measured with coil tube drilling? Is it linear footage? Is it depend on pressures that you're drilling in for different stratas? Is it certain areas that you might get more life out of a drill string than the other, or how is that measured?
There's a handful of factors that defines the life of the coil tubing. There's the material quality, there's the pressures you're running in it, there's the wall thickness. So there's a list of things that defines what you're drilling, what's your bent radius of your tubing. All of that plays into an equation that you can run in an algorithm. As I said, we have electric over hydraulics, so we are monitoring every 3 feet of the drill string, because you've with a number of you can say rated bends up against a theoretical fatigue life. So that's how we do it. So you have a pretty good idea about it, but let's be realistic about it. If you end up having a big nick in your drill string or some external damage, if it's very corroded, the fatigue life will change.
Is that something? Is the coil tube drill string something that you would plan to replace, preemptively?
Like, is there an expected life cycle? Like, I've used it so many times.
Semi-monthly.
Absolutely, yeah. I mean, as I said, for this, we schedule for 300 to 600 installations of one reel of coil. You typically start by the hardest damaged part of your tubing is typically the end of it, because for some reasons it's in and out of the borehole more frequently. So you start chopping the end of your tubing, but you don't have to adjust that in your fatigue management. So you can monitor it, and definitely yes, you plan for placement of the coil.
Replace
So
it.
I am talking about it. We're not drilling with air, so if you've seen an air hose burst, it can be a pretty aggressive thing when you have an air hose going around. Because we're drilling with fluid, it looks more like a leaking high pressure hose. So it's not that you would have a bang and a lot of things goes on. You might get wet if it totally fails unexpectedly, but it's a different experience than drilling with air.
I think to put a button or a bow on this entire discussion here is we have opportunities to adopt technologies that apply to what we want to improve this industry. And we have several amazing cases here. And as you're working, the best tool often is the most readily available tool. But when you have time to back up and think, I need to get 80 million buildings done by 2050, what is a tool that I want to invest in that could grow? And that's what we see great with Rototec and Dragon and Soren bringing this style of CoilRig, and Tunca with Celsius and Dandelion, bouncing out questions here, and Phoenix Foundation. We're better together when we go, why not? Instead of everything in this industry is a hammer, right? Like once we get past that and start thinking of it as a scalpel, we can be surgical drillers and do this in urban markets or anywhere we want and raise the level of this industry. Is that good to wrap? Yes. Thank you, everybody.